Imagine a world where the oceans eat glass. The rain is a boiling thermal event, and the local version of a fish is a bomb disposal robot hunting a refrigerator. Chemistry's dragon. When we imagine alien life, we usually begin by swapping out familiar ingredients. Ammonia instead of water, methane lakes like Titan instead of oceans, silicon instead of carbon, or sulfuric acid clouds instead of spring rain. As we've explored in our Strange Lifeforms and Alien Biochemistry episode, those ideas are strange, but still generally biological in shape. Fluorine is different. Fluorine is not just another tool in the chemistry shed. Fluorine is the tool with a warning label locked behind glass, while a chemist stands nearby saying, "No, really don't touch that." It is the most electronegative reactive element, a greedy electron thief prone to robbing any of those substances it encounters. Free fluorine gas makes oxygen look mellow and diplomatic, and oxygen was dangerous enough that early Earth life had to survive an oxygen catastrophe before later organisms learned to breathe it. Put ordinary organic matter in contact with free fluorine and usually do not get gentle biochemistry. An instant report. Diatomic fluorine is a highly toxic yellow gas. Yet once fluorine bonds to something, especially carbon, the result can be astonishingly durable. Carbon-fluorine bonds are amongst the strongest in organic chemistry. That is why fluorinated compounds show up in medicines, refrigerants, non-stick coatings, high-performance materials, and long-lived industrial chemicals. Fluorine can make molecules tough, resistant to attack, and slippery to us. It can turn chemistry into armor, so fluorine shows up in three very different forms. Free fluorine is the dangerous one, reactive, toxic, corrosive, and eager to fluorinate almost anything it can reach. Fluoride is the spent form, stable, low energy, and often locked away in minerals like fluorite and fluorapatite. And fluorinated carbon compounds are the armored form, durable, useful, and resistant to attack, but often hard for biology to recycle once they are made. That is the paradox of hypothetical fluorine life. Fluorine is often either too reactive or too stable. It can release energy too violently or lock atoms into compounds that are difficult for biology to recycle. Life needs the middle ground, chemistry that can be pushed out of equilibrium, but not so far that every reaction becomes a fire, a poison, or a dead end. Biology is not just energy release, it is energy release under control. So today we're not asking whether organisms can be made of fluorine the way life on Earth is made of carbon. Fluorine is a poor backbone for complex molecules. Carbon builds chains, rings, scaffolds, and architecture. Fluorine mostly caps, hardens, poisons, preserves, or protects. Instead, we're asking three questions. Could carbon-based life use fluorine as a tool? Could life exist in true Halogen Sea, especially when based on hydrogen fluoride? And could the most extreme life forms use elemental fluorine itself, not as an atmosphere to breathe casually, but as a dragging cage inside biological machinery? Needless to say, this is not a prediction that fluorine life is common. As we see in our looks at other possible alien chemistries, from ammonia and methane to silicon and boron, the odds still seem to favor the familiar team of carbon and water. Those two remain champions for excellent reasons. But alternative chemistry does not always mean replacing everything at once. Ammonia is usually discussed as an alternative solvent to water, not a replacement for carbon. Silicon is usually discussed as an alternative structural element to carbon, not a new ocean or solvent for biochemistry. Methane wars may still use carbon chemistry, just under colder and stranger conditions. After all, methane is made of carbon and hydrogen. Fluorine is different because the best scenarios for it rarely put in the main framework of life. It is not about replacing carbon or water so much as asking whether it could play a critical supporting role, close to the way phosphorus does in Earth life. Phosphorus makes up only about 1% of the human body, but it is central to bones, DNA, RNA, cell membranes, and ATP, the molecule we use to store and move usable energy. That is also the spirit of the 2014 paper Fluorine-Rich Planetary Environments as Possible Habitats for Life, which we are drawing on today and is well worth a read. In that, they do not ask us to imagine ordinary Earth life with fluorine labels pasted on, but rather whether fluorine-rich worlds could offer unusual chemical settings that life might exploit. Fluorine is probably not likely to replace carbon as the backbone of life. Like it is more likely to modify, protect, poison, preserve, dissolve, or destroy. That makes it seem less like swapping one ingredient for another, and more like asking whether life can build safely around chemistry that is constantly trying to become either too violent or too inert, and fluorine has a very sharp edge. Fluorine in the toolbox. I think the safest version of fluorine life is still the most recognizable. It is carbon-based. It might use water, at least internally, but it evolves on a planet where fluorine is more available, fluoride minerals are more common, and volcanic or hydrothermal systems concentrate fluorine compounds. Over time, organisms learn to use this dangerous element sparingly and carefully. This is not life made from fluorine, it is life that keeps fluorine in the toolbox. On Earth, fluorine is not especially rare in the crust, several hundred parts per million and just a bit less common than phosphorus, but biology mostly ignores it. And that's not uncommon, aluminum is vastly more abundant, and yet not a big player in biology. Chloride helps with nerve signals and fluid balance. Iodine matters for thyroid hormones. Fluoride appears in teeth and bones. But natural organofluorine compounds, where fluorine bonds directly to carbon in living systems, are rare. Earth life mostly decided fluorine was a specialty item, not a pantry staple. Incidentally, to avoid confusion, fluoride is what you get after fluorine has gained an electron or bonded into a stable compound, such as calcium fluoride in fluorite or fluoride in tooth enamel. So it is usually much less reactive and more chemically spent. We are talking about fluoride-based life today too, but as you already noted, we use fluoride in our teeth and bones already. In that very limited sense, Earth life already uses fluoride, though calling us fluoride-based life would be like calling your house nail-based architecture, and while we will focus initially on those closer to home, fluorine-based life can get pretty extreme. Carbon-fluorine bonds are hard to make and often harder to break. Once fluorine gets attached to an organic molecule, that molecule can become more durable, more toxic, or less metabolically flexible. That is useful if you are making a poison, a defensive coating, or a molecule you don't want enzymes to chew through. It is less useful if you want fast, reversible, recyclable metabolism. But stubborn chemistry can be valuable. On a fluorine-rich planet, organisms might use fluorine the way Earth organisms use toxins, waxes, shells, thorns, resins, and bitter defensive chemicals. A plant analog might lace its leaves with organofluorine compounds that make them hard to digest. Grazers might need specialized gut microbes to break them down. Predators might steal those compounds and concentrate them in venom sacs. Scavengers might become chemical specialists, able to eat carcasses that would poison everything else. From a distance, such a world might not look like an acid nightmare. It may have forests, reefs, microbial mats, grazers, predators, and decomposers. Up close, though, the grass is toxic, the bark is a fluorinated shield, the shells are fluoride ceramics, and the soil would make visiting biochemists worry their spacesuit was going to melt. Let us consider a fluorite reef. Fluorite, calcium fluoride, can fluoresce under ultraviolet light. Imagine a cold, shallow sea beneath a dim red dwarf star, where flares or auroras sent ultraviolet pulses across the water. The reefs answer by glowing in blues, greens, violets, and ghostly whites. That fluorescence is not magic alien photosynthesis, but evolution is good at turning physical accidents into billboards, signaling, camouflage, radiation management, or simply a reef that glows when the star has a tantrum. Fluorine-rich life can also make geology more edible, which is a massive resource boost. Hydrofluoric acid attacks silicates, including glass. In a fluorine-rich ecosystem, organisms might use hydrogen fluoride-producing tissues or fluoride-rich secretions to chemically mine rocks. Picture a pale stone not just eroded by waves, but grazed by life. Microbial films dissolve mineral grains. Larger organisms instead scrape softened surfaces with ceramic mouthparts. Reef builders precipitate dissolved minerals elsewhere, turning eaten geology into skeletons. In that world, the line between eating and mining blurs. We only do the organic material ourselves because it's an easier way for us to get nutrients and energy, but a tree already mines carbon from air, water from soil, and mineral from dirt. On a fluorine-rich planet, a tree might be a chemical milling machine with roots that etch stone. If meat tissues are fluorinated, dead material may also last longer. On Earth, fungi help to unlock wood as a major resource. On a fluorine-rich world, a great ecological revolution might be the rise of organisms that can break down corpses, leaves, and shells that earlier life found almost indigestible. For my part, I think this is one of the most plausible fluorine biospheres. carbon-based life using fluorine sparingly and effectively. It hardens teeth, poisons enemies, armors skin, glows in the dark, mines rock, and makes organisms less edible. This is minimalist fluorine life, and thus probably the easiest, but it's not the only option. The Halogen Sea. Most alternative approaches to life either use chemistry taking place in water or substitute another solvent like ammonia or methane in. Here, we are not imagining an ocean of pure liquid fluorine, which is so cold and reactive is more like a planetary chemical weapon than a swimming pool, but an ocean of hydrogen fluoride. Hydrogen fluoride is the obvious candidate because it resembles water's dangerous cousin. Like water, hydrogen fluoride can form hydrogen bonds, is polar, dissolves many substances, and might allow some of the transport, charge separation, and molecular encounters that complex chemistry needs. And unlike water, it attacks silicates, including glass, and all water is handled with extreme caution because it's not merely acidic but deeply toxic. And this does open the door to some silicon-based life, which we've also discussed before as an option. A solvent for life has to balance competing needs. It must let molecules move and interact but not destroy all complexity. It has to allow macromolecules, ones made of thousands or even millions of atoms, not a handful. It must support gradients, membranes, transport, catalysts, and information-bearing chemistry. Water, our universal solvent, is spectacularly good at this. Ammonia seems to be too. Hydrogen fluoride is probably worse, but worse than water is not the same as impossible, especially if we're not demanding that it produce Earth life with the labels changed. A 2024 review by Baines, Petkowski, and Seeker, Alternative Solvents for Life, which includes extensive, if not terribly optimistic, discussion of hydrogen fluoride, is useful here because it treats solvents as a set of jobs rather than a single magic ingredient. Occurrence, solvation, stability of dissolved molecules, and chemical functionality. That separation into subcategories probably deserves its own treatment if we ever felt like doing episodes specifically focused on alternative solvents for life. In the meantime, check out that paper. And in there they also note that hydrogen sulfide is one of the most common emissions from volcanoes and that it isn't miscible with water. So, on a world of frozen water ice, you could have hydrogen sulfide floating on that ice as a liquid. A hydrogen fluoride ocean world of this sort would thus be very cold by our standards. We might imagine a planet farther from its star, a twilight zone on a tightly locked world, an outer system moon, or a rogue planet warmed from below. So the sky might be dim, the weather slow, and the pale shores chemically etched. That is the key difference. In a hydrogen fluoride sea, geology becomes edible. On Earth, rock is usually the slow background. In a hydrogen fluoride sea, rock might be an active participant, constantly dissolved, rebuilt, and mined by life. Silicate cliffs, volcanic glass, and mineral sands could become chemical buffets. Microbial mats might cling to etched stone, concentrate hydrogen fluoride, dissolve tiny amounts of rock, extract silicon, metals, phosphorus, fluorides, and trace nutrients, then precipitate new minerals behind them. Larger organisms might follow. Some scrape softened stone with ceramic mouthparts, some burrow chemically. Predators might spray a reactive fluid that weakens a prey animal's shell. Reefs might grow where dissolved minerals meet the right chemistry and precipitate into fluoride skeletons. This is the glass-eating ecology. Stone that grows, cliffs that crawl, reefs that are half organism, half chemical mining operation. Not completely unlike home either. But the organisms themselves would need very different boundaries. A normal Earth-style lipid membrane exposed directly to hydrogen fluoride may not last or function properly, so hydrogen fluoride life would probably need chemically resistant barriers. Fluoropolymer-like skins, mineral shells, ceramic tissues, and protected internal compartments. To us, those surfaces might seem slick or non-stick. To native organisms, they may be ordinary grip. Life is boundaries. A cell has a tiny rebellion against the universe, a bag of chemistry saying, inside here we do things differently. In a hydrogen fluoride sea, that boundary must resist the solvent, preserve the gradients, move nutrients, dump waste, and prevent the organism from becoming a regrettable chemistry demonstration. Hydrogen fluoride life might be more chemical submarine than water balloon. Its bones and shells might use calcium fluoride, magnesium fluoride, metal fluorides, fluorapatite-like materials, or mixed silicon-oxygen fluorine composites. A large hydrogen fluoride sea animal might less resemble flesh and more resemble a flexible ceramic wrapped in chemically resistant hide. Predators might need hooks, harpoons, suction pads, or chemical glues just to hold prey. Our next challenge I think we should discuss is energy, which is a tricky topic in hypothetical low-temperature organisms. A hydrogen fluoride ocean is likely cold, and cold slows chemistry. Fluorine chemistry can be energetic, but that does not mean life is hyperactive. A stick of dynamite contains plenty of energy, yet it is a poor model for metabolism because it does not pace itself. Hydrogen fluoride sea ecosystems might rely on mineral catalysts, geothermal vents, electrochemical gradients, radiation, or redox reactions involving fluorine, sulfur, phosphorus, metals, hydrogen, methane, or silanes. At a vent, reduced compounds from the interior meet oxidants or reactive halogen compounds from the ocean. Temperature gradients and mineral surfaces give life a place to cheat. There may also be flare-driven photochemistry around red dwarfs. Carbon tetrafluoride is extremely stable, so any photosynthesis-like cycle using it would need high-energy UV, extraordinary catalyst, or unusual geochemistry. But active red dwarf flares could create reactive compounds that life harvests later. Their spring might be a stellar tantrum. And then there is water. To us, water is the symbol of habitability. Follow the water, we say, and for Earth-style life that is excellent advice. But to an hydrogen fluoride sea organism, water might be contamination, poison, or catastrophe. Hydrogen fluoride and water can't mix, so this is not simply instant explosions, but a biosphere adapted to low-water hydrogen fluoride chemistry could be disrupted by water changing acidity, salts, membranes, minerals, heat flow, and chemical gradients. So a water storm isn't just a chemical contaminant, it's a thermal event. It's rain that releases heat as it reacts with the ocean, effectively boiling the local ecology while it poisons it. On Earth, rain brings life. On a hydrogen fluoride world, children might be told stories of the old days when the sky fell white and the reefs screamed. If we send a probe into such an ocean, we might not see fish at first. We might see stone that grows, reefs that glow, cliffs that crawl, and pale films that etch glass. We might see armored shapes avoiding contact because contact is chemistry and chemistry is danger. Hydrogen fluoride life is not likely, but it reminds us that habitability is not a single recipe. Life needs gradients, structure, memory, and controlled reactions. Water is excellent at that. Hydrogen fluoride would be harsher, colder, and more dangerous. But worse is not the same as impossible. Rocket engine biology and fluorine dragons. Now let us consider life that deals directly with elemental fluorine. This is the least plausible version, but also the most visually irresistible. Elemental fluorine is a pale yellow gas under ordinary conditions, a liquid only at very low temperatures, and one of the strongest oxidizers known. For Earth life, it is not an environment, it is an emergency. If there are literal seas, clouds, or thick atmospheres of elemental fluorine, we are probably discussing cryogenic worlds, outer system bodies, rogue planets, dark moons, or exotic planets with unusual pressure and chemistry. These are places where ordinary water is rock, familiar gases become liquids or solids, and Antarctica looks like a sauna with penguins. Yet fluorine is tempting for metabolism for the same reason it is terrifying. It is an extraordinary oxidizer. If an organism could control reactions with fluorine, it might extract large amounts of energy from reduced compounds. But if it could control, it's doing heroic amounts of work. A flamethrower also contains useful energy. It does not mean you should install one as a digestive organ without a robust warranty. Fire-breathing dragons are awesome in stories, but make little sense from an evolutionary perspective, at least with terrestrial biochemistry. I should also note these creatures would not have lungs in the familiar sense. They would need reaction chambers, ceramic-lined sacs, fluoride mineral walls, sacrificial membranes, chemical valves, heat exchangers, and catalytic surfaces that permit reactions only at specific places and times. A metabolism less like a stomach and more like a rocket engine. The organism might store fluorine or fluorine-rich oxidizers in isolated compartments, separated from fuels by barriers that must never fail. It might circulate inert fluids by allowing high-energy reactions only inside mineralized organs. Waste must be removed, heat dumped or captured, and damage repaired constantly. In other words, the body is built around containment. This is why elemental fluorine life should not be pictured as fast and hyperactive. Powerful reactions are not the same as safe reactions. When your chemistry is difficult to control, the safest strategy is slowness, precision, and isolation. A fluorine predator might spend days motionless in cryogenic seas, looking like a pale ceramic stone before leaping into action for a few brief moments. Though we might also ask, what is it hunting? It may get many of its minerals simply by bathing that sea or scraping the seafloor. The biology here might be more vampiric, hunting for cryo substances to suck out of prey, so maybe less like a lion hunting a gazelle and more like Count Dracula hunting a refrigerator. Though vampires would not do well on such planets either, as all that fluorine chemistry would make familiar ozone protection unlikely, or at least very chemically complicated. Dracula would not be the only one getting a 10 as a result, though since this is probably a quarter ward anyway, the UV levels might not be disastrous simply because there's less sunlight in general. Still, it is basically inherent to ultraviolet light that it wrecks molecules. Organisms can get around that with thick outer skins, but anything trying to run on photosynthesis needs some way to minimize UV hitting its delicate parts without blocking too much useful sunlight. I keep mentioning these life forms eating glass, and part of that comes to mind because glass, like the stuff in your windows, blocks much ultraviolet light while letting normal visible light through. So if we're already contemplating an organism that eats glass, having it excrete that material as a protective covering for its leaves does not seem too wild. Beyond sunlight for energy, the broader fuel storage problem is important. Fluorine needs reduced compounds to react with: hydrogen, protected hydrocarbons, reduced sulfur or phosphorus compounds, metal hybrids, or perhaps silicon hydrides. Silicon-fluorine bonds are very stable, so reacting silicon compounds with fluorine can be energetically favorable. But stable products are a double-edged sword. Life needs cycles, not one-way trips to chemical retirement. If metabolism produces dead-end fluoride salts, the planet needs a reset mechanism: ultraviolet flares, geothermal vents, electrical storms, deep crustal chemistry, or symbiotic chemical salvage. As such, ecosystems might be episodic. Flare, volcanic pulse, or seasonal cycle creates reactive nutrients. Life blooms, feeds, reproduces, then retreats into dormancy. They are equivalent to day and night or seasonal cycles, so they might have very long periods. Their bodies would be extreme: fluoride minerals, fluorinated polymers, ceramics, segmented plates, bellow-like joints, and protected internal gels. It might look like living pottery, armored worms, ceramic squids, or mineral insects, hard to distinguish from rocks until they move. Even death changes. On Earth, a corpse is food. In a fluorine environment, a corpse might be a hazard. Though I suppose that's often true here, too. If containment organs rupture, stored oxidizers and fuels can react. A battlefield on such a world might not rot, it might hiss or even explode. Elemental fluorine life is probably an edge case, if it exists at all. It is far more likely that fluorine appears as a tool, solvent component, mineral, or ecological hazard than as the direct breath of animals. As a thought experiment, it is a magnificent idea, but in terms of practical life forms, my guess is that most of the time it probably ends very badly. Roads, weather, detection, and civilization. Now that we know what such life might look like, the next question for us to consider is, where do we find worlds like this? Well, I guess they'd probably not be warm Earth-like planets in Goldilocks zones, especially our more fluorine-intense versions. Better settings include cold terrestrial planets, outer moons, rogue worlds, or twilight zones on tightly locked planets around dim red dwarfs. The habitable regions might not be a blue-green belt of rivers and forests, but a cold halogen shoreline under a fixed red sun. Imagine such a world then. To one side, bright cliffs and reactive deserts. To the other, eternal night and frozen volatiles. Along the middle, pale hydrogen fluoride seas, white fluoride beaches, fog banks, etched stone, and fluorite reefs that glow when the star flares. A rogue planet might hide hydrogen fluoride-rich brines under frozen crust. A moon might have localized halogen basins and volcanic activity. The first fluorine-rich life might not need a whole planet of hydrogen fluoride, just a niche where fluorides, acids, minerals, and energy gradients meet. Fluorocarbon seas are another possibility. Perfluorocarbons can be chemically inert and dissolve large amounts of gas. They may not be good solvents for life's main chemistry, but they could serve as an external medium or respiratory reservoir. The open ocean might look sterile while vents, cracks, and interfaces crawl with life. Weather on these worlds would be chemistry with a forecast. Hydrogen fluoride rain could etch exposed minerals. Halogen fogs could carry reactive compounds. Fluoride salts might precipitate as snow or frost. Chlorine or bromine compounds might tint clouds yellow-green or red-brown. A local forecast might warn of water ice contamination, rising metal fluoride saturation, and a strong chance of shell erosion after sunset. Water storms are the great reversal. To us, rain is life-giving. On a halogen world, water may be a pollutant, disaster, or mass extinction trigger. A comet impact, volcanic release, or seasonal shift could dump water ice into a hydrogen fluoride-rich environment, changing acidity, salts, membranes, heat flow, and chemical gradients. A freshwater spring might be a toxic waste leak. A glacier might be a sleeping catastrophe. Therefore, from far away, such worlds might confuse our search for life. Fluorine-rich atmospheres could contain hydrogen fluoride, carbon tetrafluoride, sulfur hexafluoride, and other fluorinated gases. On Earth, carbon tetrafluoride and sulfur hexafluoride often suggest industry. But on a halogen world, they might be techno-signatures, but also geology, biology, or atmospheric waste. Alien planets do not sort gases into folders labeled life, industry, and weird rocks. A techno-signature of one planet might be swamp gas for another. So civilization on fluorine-rich worlds would follow different materials. If its environment attacks silicates, easy glass may be unavailable. No glass means no familiar windows, lenses, microscopes, telescopes, vacuum tubes, or laboratory glassware. Astronomy, optics, chemistry, and electronics might be delayed, or approached through polished crystals, fluoride minerals, ceramics, protected metals, biologically transparent materials, or instruments grown rather than blown. If metals react with fluorine or form brittle fluoride layers, metallurgy may also be altered. If water is poisonous, familiar chemical processes become hazardous. If the world is cold and reactive, heat management, sealing, and corrosion resistance become foundational technologies. So they might not have a Stone Age, Bronze Age, and Iron Age in our sense. They might have a fluoride age, a ceramic age, a sealant age, and only later a metal age. Their Prometheus might not bring fire, but corrosion-resistant plumbing. Rocketry is the perfect paradox. Fluorine is an excellent oxidizer, so in principle they may have access to powerful chemical propulsion. But in practice, rockets are not just fuel and oxidizer. Rockets are pumps, pipes, seals, chambers, nozzles, controls, insulation, and materials being asked to tolerate catastrophic conditions. They might discover the rocket equation early, then spend 10,000 years inventing a gasket that does not become part of the exhaust plume. Spacecraft also flips life support. Human spacecraft carry warmth, pressure, oxygen, and water. A fluorine world spacecraft might carry cold, dryness, hydrogen fluoride, fluorocarbon fluids, halogen atmospheres, and chemically inert compartments. A habitable module for them might look to us like a cryogenic chemical storage tank. A habitable module for us might look to them like a sauna full of oxidizers and liquid poison. One could imagine picking up native microbes on accident on such a planet and having them infest your cryogenic systems. We call Earth habitable because it is habitable for us. Habitability is local. To us, a fluorine world is a death planet. To its natives, it's home. This month we've been talking about outsider aliens, dangerous species, fluorine-based life, and creatures shaped by environments very different from our own. But whatever chemistry life uses, evolution still rewards the builds best suited to the local environment. That's the idea behind TierZoo Remastered, which treats the animal kingdom like a competitive game, ranking species by their abilities, weaknesses, and ecological strategies. Its remastered, classic shark and whale tier lists explore two very different groups that have dominated the oceans through speed, size, intelligence, teamwork, specialized senses, and some extremely effective builds. It's a fun way to explore zoology, but also a useful framework for reimagining alien ecosystems, like void sharks and space whales. Strange features are not there merely to look exotic, they are adaptations shaped by the rules of their world. You can watch TierZoo Remastered on Nebula, on my full SFIA catalog, monthly exclusives, bonus episodes, and regular episodes early and ad-free. My link or the QR code gets you 50% off an annual plan, or 40% off lifetime access. Life under armed guard. Fluorine life is probably not the default path for biology, but I could easily see it having a more extensive role in life than it does, and again it has a minor role as fluoride in our teeth and bones. It is a heavy lift to expect to have a big role, even more so than sulfuric acid or ammonia. Again and again we see carbon and water remain the safest bet. Carbon is flexible, versatile, abundant, and capable of building complex backbones. Water is common in the cosmos and excellent at supporting the delicate mess of charge, folding, transport, and reaction that biology needs. But safest bet does not mean only game in town. We must also acknowledge that our ability to model this with accuracy is terribly limited, so it might be much easier or harder than we think. But I would stress again that fundamentally fluorine is difficult because it is powerful in the wrong ways. Free fluorine is too reactive, fluoride is too spent, carbon-fluorine bonds can be too stable, silicon-fluorine bonds can be too final. Life does not live at endpoints, it lives in gradients, cycles, halfway states, controlled leaks, stored energy, repair mechanisms, and molecules can be built today and unbuilt tomorrow. A dead battery is stable, ash is stable, salt is stable, a fossil is stable. Life is trying to be stable enough to persist and unstable enough to do something interesting before lunch, or before becoming lunch. So our three scenarios are really three ways to manage a dangerous dragon of an element. Fluorine-rich carbon life uses it as a tool to harden teeth, protect shells, poison leaves, or resist digestion, to color minerals, mine rocks, or make durable spores and skins. And I see no constraint on this being fairly common and even more abundant than here on Earth. Our second, hydrogen fluoride solvent life makes the Halogen Sea itself into a habitat, surviving through armored boundaries, ceramic tissues, compartmentalized chemistry, and glass-eating geology. The third, elemental fluorine life, the least likely but the most dramatic, would require sealed reaction chambers and rocket engine metabolism, biology built around containment. Across all three, the same lesson repeats. Life is not a substance. Life is organization. It is not water, carbon, oxygen, sunlight, or warmth by themselves. Those are ingredients and conditions. Life is what happens when chemistry builds systems that maintain themselves, copy information, harvest energy, regulate boundaries, and adapt. If fluorine helps with those jobs, it may appear in life. If it interferes with too many of them, life will avoid it. If we ever found such a biosphere, it might not announce itself with green forests and pale oceans. It might be quiet, cold, pale, chemically weird. It might look like geology until it grows, like corrosion until it reproduces, like frost until it hunts. A creature from a hydrogen fluoride sea might look at Earth and see a nightmare, oceans of metabolic poison, skies full of oxidizer, tissue-wrecking temperatures, and rain falling like a planetary solvent attack. It might describe us as bizarre extremophiles that evolved in a corrosive oxygen-water atmosphere and somehow learned to enjoy thunderstorms. And it would not be entirely wrong. From its perspective, we are the weird chemistry. So no, fluorine life is probably not common. It may not exist at all, but it asks whether life can domesticate one of the most dangerous elements, not by taming it into gentleness, but by confining it, channeling it, weaponizing it, and surviving beside it. And if the answer is yes, then somewhere in the dark may be creatures of the Halogen Seas, armored like living ceramics, mining cliffs with acid mouths, grazing on glowing fluoride reefs, and regarding water with ancestral terror. They would not be soft, they would not be familiar, they might not even seem alive at first, but then they might move. Life is chemistry under management. Fluorine life will be chemistry under armed guard.